At the time of this recording, we have April 2026. And if we go back 1 year, then MCP servers were the new tool that everyone was using. Nowadays, some people even say MCP is already dead and we should use skills instead. And we also see this for other terms. For example, coding assistants, and nowadays it's harness engineering and other stuff as well. So in AI, we have a lot of hype, but we also have to say that the AI field development is extremely fast. And there is, for obvious reasons, this fear of being left behind. And what I always think what really helps if we understand the fundamentals, because the fundamentals usually don't change that often. And once we grasp them, then it's also easy for us to understand what happens at the outside. And this is exactly what this video is about. So at the core of AI, we have the model, obviously, the LLM or the large language model. We or I, together with you, will see how those models are created, which is the training process or the training phases. We also see how the model then work, which is what we call inference. And once we have covered that, then I think it should be easy to understand the limitations of the models and also all the tools around it which try to mitigate those limitations. And I would say there are 3 types of limitations. First of all, the model can only produce text, nothing else, which means if we want that the model is doing more than just producing text, there needs to be something else. The model is also lacking up-to-date information. So data actuality, which is also a very important topic. If I want to ask the model about the latest news, it should still be able to answer me. And what we also have is the context size, the context engineering, because we can't just put everything into the model what we want. There is a limitation to the input as well. And that being said, welcome to this video. My name is Rainer Hanekamp. I'm a Google developer expert. Usually I do more with Angular, so on this YouTube channel you will find a lot of Angular videos also in the future. But I also have now a role in Solverius AI, which I founded together with my colleague Murat Sari, and I will say a little bit about it at the end of this video. So before we start, a very important disclaimer. All the examples that I bring here, they are extremely simplified. Don't think that this is the way how it works in the real world. It's just about to transport, to communicate the principles so that you have an idea on how these things work. So when a model is generated, then we usually say we are training a model. There are multiple training phases. And the first one, and also the most expensive one, is what we call the pre-training. And this is the phase where the model is fed with text most of the time. Modern models can also consume videos, audios, or some other data. But let's just say, for the sake of simplicity, we are feeding only text to the model. And you see here one example text like Murat lives in Leum and maintained Ogre. Rainer is from Österreich, which is the German word for Austria in like Star Wars, and so on and so forth. The model obviously needs to do certain calculations with that text. And it can only calculate if it has numbers, which is why the model first has to map this text into numbers. And it does this by using tokens. What we see here is the same text again, now split up in tokens. You see this with this colored marking that we have. And what happens then afterwards is that each token is then assigned a number. And this is then actually what the model then sees. So in the end, the model doesn't see the text, but the model sees just numbers. That's it. When it comes to the tokens, I want to make you aware of a few things. First of all, a token represents or can represent a full word, but it can also represent parts of a word, syllables, or maybe just one character, as we actually see here in the name Murat, where the first character, the M, is a token on its own. Second, tokens are also language independent, which means we can mix multiple languages together. And it's also what we see here. For example, Österreich, in the middle, it's one token. It has a lot of characters, but it is one token. Whereas in Leoben, we see it's kind of split up into two different tokens. So two tokens make up that Leoben. And the rest is English. So that just works fine. We also see that the tokens can also represent non-existing words. For example, there is a typo in hobby, as you see. We write hobby with two B's. I even know this as a non-native English speaker, but it's not really a problem for the model. It can also represent a hobby with tokens as well. And the last thing is that even white spaces play a role. Because, for example, if you look closely at the first sentence where it says ogre and then there is a dot, there is a new line after the dot. And you also see that the number of the token is 558. Whereas the other two dots, after Star Wars and after profession, they have the number 13, which is the reason because there is no new line at the end. So this is something you should also keep in mind. And of course, you can also take a look at those numbers. You see here that usually the English characters, also English words, they usually have lower numbers, whereas words coming from non-English languages have much higher numbers. For example, Austria here has 70,997. And for example, the M has 44. Also R has 49. So you see already that there is a system behind it. There could be differences between the models about the tokens, but in general, the tokens are defined per model, and that's the way how it is. So our model gets now that text, and then starts the pre-training phase. And the way how it works is that we or someone presents the model with, let's now just say again for simplicity, each token is just one equals one word. I'm giving the model now the part of the start of a sentence, which is Murat. And now I'm expecting from the model to be able to predict the next word, the next token. And the model has, of course, no clue. It has no idea what it should do. And that's why at the beginning, it just starts with wild guesses. So it takes all the tokens that it has, which means it could say Murat is, Murat Star Wars, which is actually two tokens, Murat Renner, does also not fit, and so on and so forth, until it makes the right guess. And then I can tell the model Livs is the correct one, and internally the model can then make certain actions to kind of, I don't want to say remember, but there are certain things going on where the prediction for the next time would hopefully not take that long. Let's put it like this. Again, very simplified everything. Once this is done, then we continue with the next part. Then I say, and now I have Murat lives. What's the next token? And then again, the model starts to guess, and if it makes the right guess, then we tell it this was the right one, and then the model internally will process this information somehow. And this is the way how it works. Of course, there are now a little bit more than just these 2 or 3 sentences which are fed into the model, but this is the way how the model is trained. And there is now a very important thing about this training phase, about the pre-training, because this can be fully automized. I don't need a human being to tell the model kind of the first part of a sentence and then also tell if it has guessed it correctly or not. This can be fully automized, which means I can extremely scale up the pre-training phase as long as I have the necessary machinery, obviously. This is also why I said actually in the beginning, pre-training is extremely expensive because you can fully scale it up. It's really like an unsupervised training that we see here, or not supervised. But while we are training the model, while it is making those kind of predictions, something happens. The model starts to take all these tokens and starts to see certain relationship between them, but also identifies certain patterns. For example, it could find out that maybe Murat and Rainer, as we know, these are names, but then the model via the training could find out that there is a certain relationship between these two, that in certain patterns they are used in the same way. So it starts to add certain dimensions to the model. And it could, for example, have a name dimension where Murat and Rainer are quite close together and the other tokens are actually very far away. But it also does this to all the other tokens as well, which means it could also see that Leoben, Österreich or Austria, that they might represent locations, geographic things, and it would then maybe have a dimension for that as well. Yeah, so again, it during the training phases, it starts to develop certain patterns, certain dimensions, which can help it to predict things better. Which means, if we will now present the model with a sentence that it has never seen before, like for example, the Nanje lives in, and let's not just say the model has never seen that sentence in the training data. Then what happens now, and actually the process where the token predicts it, also then for us when we are working with the models, but also during the training phase, the process where the new token is predicted is called the inference. So that's a very common term that you hear very often in AI. So let's just say the Nanje lives in, and the model should now predict the next one. The model has been trained on sentences like Murat lives in Leoben, Rainer is from Austria, and others. But somehow it sees now, oh, this Murat and Rainer and the Nanje, they are kind of very close. It seems that they are actually part of the same dimension, or very close when it comes to those names. And it then identifies or sees this pattern that it has already learned before from the other two names. And it would now say, according to those training data, to the patterns that I have identified, the next token should be something from this location dimension. And the model would then say, I have Delhi, I have Austria, I have New York, I also have Leoben. So these are the tokens that are kind of in my location dimension, which means that it would start to come up with a probability list, or with a list where it says these are the tokens where there is a very high probability they are the right ones. The question is, how does the model now come up with the probabilities? Because it has to now assign probabilities to Austria, New York, Delhi, or something else. For obvious reasons, the model has a lot of dimensional data. So it could be that there is a dimension for German things, for Indian things, and then maybe also for US things, which you see here. German things could be Alps, Rhine, Deutsch, or just Rainer, the German first name. And in the Indian dimension, there could be Delhi, Vishnu, also the Nanje, it's also like an Indian term, and some others. And because the Nanje and Delhi are in one dimension, but Delhi also is in the location dimension, the model could now say the highest probability of the location dimension in this case would be Delhi, because that kind of fits. That does not mean that the other locations are impossible, but they just have not the same probability as Delhi. So that's key here. Common sense would now say, well, the model should just take the token with the highest probability. But that's not always true. Before we come to that, I think maybe we just pause here and kind of think about it, that this actually means that the model is really able to produce, to run inference and produce information, data or sentences which it has never seen before. Because very often there are certain myths where we say, yeah, if, for example, if we do coding or something, that we say, yeah, this pattern has to have been written already somewhere, so the model is just taking something from its training data and it applies it to our code as well, which is not true. The model is just trying to identify, it tries to assign our code or our sentence into a certain pattern, and then it just looks in its own learned patterns which ones of those are fitting, and then it just again comes up with those kind of probabilities. Which also means if you, for example, add now certain credit card informations and you say my credit card, if you tell this to a model, my credit card is 123 or something, and someone else is then asking, do you know the credit card of that guy? And the model has been trained with the data before, then you don't really have the guarantee that the model is able to tell you the credit card, because it's not a lookup table. It's a huge pattern recognition machine. That's what the model is, based on a lot of statistics. Yeah. So again, the model is also able to come up with new things it has never seen before. And because of these dimensions, of these certain relationships, of this understanding, the way how we use language, the way how certain things relate to each other, it could be the case that the model also starts to innovate things. Yes, that's true, but it's always kind of based on the probability and based on patterns that it has learned. Now let's move on to the next thing, how the model is now actually able to select the actual token or the actual word. Here a very important term comes up, which is the temperature, which means the more the temperature goes to the value 0, the model takes more the one with the highest probability, and the more the temperature goes away from 0, larger than 0, then the more the model is starts to introduce randomness. So it also can take now certain words which have a lower predictability or probability. And that's something you need to know, because there are certain tasks where you want that the model is very deterministic, which means you will have a very low temperature. You always want to have the one with the highest probability. But then you also have certain tasks where you want that the model is very creative. And then you would actually motivate, you would allow the model to come up with predictions with lower probabilities. And this is again, if you're looking for certain ideas, or if you want to have, I don't know, some new ideas or some new insights, creativity, then you actually want to have a high temperature. And there is also another term which is maybe even more popular, more famous than temperature, but closely related to it, and that's the hallucination. So when we say the model has now said something wrong, it has lied to us, then we usually say it starts to hallucinate. But in the end, by now, you should understand that the model is not really lying. There are just certain settings given temperature where the model just to predict something which doesn't have the highest probability. And in this case, we could lower the temperature. That could be an idea. But of course, it could also be the case that the training material that the model has received was not, let's say, in the best shape, depending on the information sources that it has received. So if it's kind of comes up with, it has been trained on certain fake news, then of course it will also start to hallucinate, even if it has a very low temperature, but that's just then due to the training material it has received. To me, actually, hallucination is something which is relative. depending if I want it to hallucinate or if I don't want to hallucinate it. Because in the end, if I want the model to be very creative, then I actually want it, I encourage it to hallucinate in that sense. But don't say that. We usually assign or associate hallucination with a very negative thing. So it's not for creativity. Yeah, in the end, this is how inference works. And there are now some other things that we need to be aware of when it comes, first of all, to the training phases of the model, but also to its inference. And I think one very important aspect is the chain of thought. Before we come to the chain of thought, there are different phases, training phases, which I have already said. We have already covered the pre-training, which, as you see, there is no human required, so it can do this fully automatically. But the other phases, the fine-tuning and the reinforcement learning, they usually come with humans. So someone needs to be there and needs to tell the model if this prediction is the one that it actually wanted to hear or wanted to read. Generally speaking, we say pre-training phase is more about, I have to be careful when I say the model understands the human language, because it doesn't really understand it, as you hopefully understand by now, because you understand, the model doesn't. It's more or less about the next token prediction based on human language. Fine-tuning is about the model getting more domain knowledge. So you could then feed it with a lot of, specific data like history, art, engineering, literature, whatever you want. And of course, generally speaking, the large language models, those that we use, Gemini, GPT, or also Opus from Anthropic, they are more general purpose models. So they have been trained in all disciplines, and that's why they know almost everything. But in fine-tuning, you can also if you don't have these large models, but you have a very small one, then you can also fine-tune it for a very specific domain. They are becoming domain experts. And in the reinforcement learning phase, we say the model that's the tonality, the way how it responds, the style, if it's very polite, maybe impolite, these kind of things. I always say this is where the character of the model is formed. That's what I would usually assign to reinforcement learning. And what happens actually via fine-tuning and reinforcement learning is this very important chain of thought, which is also known as the thinking process or reasoning. I'm sure you see this all the time when you're working with ChatGPT or some other models, some other harnesses or agents, where they start to think about certain things, and this is what is generated here in these two phases. Let's take a look why this chain of thought is so important. Let's say we have a mathematical question. We ask the model what is the square root of 4. And let's again say the model has already been trained before on other mathematical tasks, so it has already seen the proper answers. By now, you know that the model is not calculating these things. The model just sees this as certain patterns, and it just tries to apply those kind of patterns with this next token approach. So it doesn't really do the square root of 4, it just tries to narrow it down. Which is why we very often, if you go back in time, you have all those kind of jokes going around where people ask the model extremely simple mathematical questions and the model was not able to answer them. Of course not, it is doing pattern matching, not deterministic mathematical calculations. A very important example is the strawberry thing, where you ask the model how many R's are in a strawberry, and the model just says 1 or something, so a wrong answer, so to say. New models don't do this. They will always give you the right answer, and they're also able to do mathematical calculations right. So they will give you the right answer for square root of 4, for example. But how does it work? Via chain of thought, I as the user, if I ask the model something, then the model doesn't try to immediately apply that pattern matching to its final answer. What the model does instead, it asks itself, like, what would you do? What instructions are necessary to solve this? So it's like of indirectly asking it not for the direct answer, but what steps are necessary to give an answer, which is what they actually call it starts to think. That's the thinking phase now. And in this case, it could be that the model says, oh, that's a mathematical task. Maybe best is if I run a simple script. You can also write actually a script that also happens. I execute it, and then I just return the answer. Those instructions that you see here, of course, this is simple text. So the model itself returns another text, which again is then used by the model to say, okay, if this is what you need to do, then please do what you just said. Write that script, execute it, and return the output of that script to the user. That's the final answer. That's your answer that you see also then in the chat. So in this case, we're getting the number 2 of the square root of 4. There is one important thing which we come back later, but the question is, if the model can only produce text, how can it actually write scripts, execute them, and read from that? That's a different thing. Let's just leave it for now. Now, before we move on to the limitations, there are a few analogies that I want to come up to give you an idea about the scale, about the amount of data we are talking about. First of all, you very often hear models are black boxes. We don't know what the model is doing. Yes and no. It's not like black and white. It's more like in a grayish zone. And I always like to compare it with the weather. We know how models do inference. We know the technical background of it because, of course, someone has to implement all that stuff. So we know how a model works. The problem is the amount of data which is moved in inference. And this is where I usually say it's the same with weather. We know what happens when it rains, when it snows, when there is a thunderstorm or something like this. We know the physics. We know exactly how these things work, but we still can't predict the weather because there are so many factors which influence each other, which just makes it impossible to kind of really predict the weather. In some way, this is also the way how it is with those large language models. It's just too much information. Next, the model does not understand you in the way how a human does. So you can really use it, you can talk with your feelings about it, it will respond in a very nice way, and you really think it understands you, but it doesn't. It just gives you the illusion, it just mimics the behavior that it has learned. It doesn't really understand you. And I very often compare that with actors that do certain things which they can't do. For example, from the movie The Pianist, you see here Adrian Brody, which is playing a piano concerto. And if you watch him, you really have the impression that he really is able to, that he actually plays it. But in the end, he has perfected the mimics, the way how he moves with his hands, with the fingers, also the gesture he makes with his face, with his whole body, like a real pianist. But he is not one. He's just mimicking it, and he doesn't really feel the things, and he also can't do it like a real one. So keep this in mind. It's you think, as the watcher of that movie, you think he's a pianist, but he isn't. It's just the level of illusion is so perfect that we are, I don't want to say fooled, but that we might get a wrong idea of the way how the model works. Next thing, model is stateless. This is maybe which comes as a surprise. Model can't remember anything. You put something in, it gives you something out. This is the way how inference works. We give it a text, it gives us back certain tokens, output tokens, until it decides now it's over. The sentence has been finished or the question has been answered, and that's it. And as you know, this is not the way how we kind of experience it when we are working, for example, with ChatGPT. If we have a session, it is able to answer, and it is able to refer to things which I said it maybe at the beginning of the conversation. It can also happen that it can refer to something which I've told it half a year ago. For example, I had an injury and it still asks me today, how are you feeling? Is this already better? And so on and so forth. So how does this work if I say the model is stateless? The thing, how it works, is that in the chat, the complete conversation history is always loaded together with our current prompt into the model. So the inference always gets as an input the whole conversation and answers on top of that. It does not remember anything. Very important to remember, which means the more often or the more chit chat you have, so the livelier the conversation comes, the more answers and responses you give, of course, the amount of the inference always increases because the model has to process everything. Remember that, because you have to pay for the model itself, you have to pay for the tokens, and it plays an important role how often you ask it something, especially if the conversation history is quite long. And for the next one, I have been thinking for a very long time, because I want to make you aware of the amount of training data a model has received during its pre-training. At the moment, GPT 5.5 has a maximum context size of 1 million tokens. A little bit more, but let's just say 1 million. You should never use that 1 million. It's just, I would say it's more like a theoretical maximum. If you want to break it down to words, then we have to say it depends on the language. But in the English language, that would be around 700,050 words, 50. The amount of 750,000 words is what you would find in the Holy Bible. So I think every one of you knows what the Bible is. Hopefully you also have an impression of how big it is. It's quite a lot in it. And you can say this is the amount of data which a model or inference can actually process. It's the amount you can put the whole Bible into it, so to say. For the pre-training, the training data, the whole amount of the training data the model has seen, we have to say 1 Bible per week. So if we say the model is trained and it takes 1 week to train it with 1 Bible, then it took it 270,000 years of training to reach the state, to have seen all the training materials that a modern frontier model has been trained on. So that would be 1 Bible per week for 270,000 years. And if you think about it, what that means, 270,000 years ago, that was the time when human Homo sapiens actually left Africa to spread out into the whole world and to develop what actually we are. So such a time period are we talking here about. And someone needs to read the Holy Bible each week until now. And then the person would have been able to process all the training information that the modern model has. But not just reading it, please. Also being able to predict it. Training doesn't just mean reading. It's also about predicting the next token, the next word. So again, this is a sheer amount of data which I almost can't really comprehend. And then a few numbers at the end. So the vocabulary size of GPT is around 200,000 tokens. So you have seen this already before. We have very high numbers. Those tokens exist, there are not more, and with those tokens you can cover each language in the world, each word, even if those words do not exist. For the latest version, GPT-5.5, as I said, the context size, the maximum is 1 million. And about the prices. Remember I said model is stateless, so you pay for the tokens you consume. The price for 1 million input, that's the Bible. So for one Bible, you are paying, if you input it, $5. And for the output, you are paying $30. So if you say you want the model to write something of the size of the Bible, then you pay for it $30. Then, if there are certain differentiations in GPT's models, so it could even become more expensive. I think if you exceed 270,000 tokens, so you're not anywhere close to the 1 million, then the price jumps to the almost double. But yeah, just to give you an idea, you pay for one input of the Bible $5, and for the output for writing it, it's around 30. Prices for tokens increase. So expect in the future that one's going to be much more expensive. How much does it cost to train a model? This is where we start with a little bit speculation, but we know that Gemini 3, that one of its models was calculated with $191 million, but that's the final run. When you include everything else, the test runs, the personnel, the staff, the resources, the hardware, the machinery, then we usually say the final run makes up about 10 to 20% of the total costs for the model, which means given the test run was around 191 million, between 10 and 20% total costs would be 1 billion, almost 1 billion, up to maybe even 2 billion. And as I said, tokens price increase, but so will also the costs for the training. So we can expect that the current frontier models have maybe cost already a little bit more. And also about the sizes. Again, we don't have official numbers, but for Llama 3.1, it's around 754 gigabyte uncompressed. That is important, because you can also compress it down. And for Gemini 3, GPT 5.4, 6 terabyte up to 40 terabyte. So you can't just run this on your local machine. That's not really important. And I think if you see those kind of numbers, then it also gives you then an idea why we always hear it's so expensive. We need to build up our own nuclear power plants. We need to have so much money and all that stuff. And of course, also why the tokens will become expensive, because you have to put in all that money. That's an investment, but you also have to earn it back. So I hope that by now that you have a better understanding how Inference works, how the models are trained, what this is all about, what you can expect from the core model itself, and then also have a better feeling of its dimensions, especially with the last numbers that I gave you. Now we come to the limitations and how they are generally fixed. And we only scratch here the surface, because all the tooling that I will quickly just mention, are huge topics on their own. So let's come back to the chain of thought we had before. So I was saying that if I ask the model about the square root of 4, the model will ask itself, how would you solve this? What are the necessary steps? What are the instructions? In this case, the model would come up with the idea to write a script. But how can the model write a script if it can only produce this text? There is no way to do that. And this is why the first limitation, that the model can only produce text, is usually solved via agents and tools. So when we communicate with the model, there is always the agent in the middle. The agent takes our message and passes it on in a format that the model can also understand. The model is not the chat, that's the agent that we see. Before the agent does that, the agent also introduces itself to the model and says, and by the way, I am an agent. I provide you certain tools. I can do certain things for you. So the agent acts on behalf of the model, which is a good metaphor. That's also why it's actually called the agent. And in this case, the agent could tell the model, look, if you want, I can write to a file. I can also execute certain files, scripts, and I can also read from the CLI, just for you to know. And of course, when the model is now remembering this, because, sorry, it's not remembering it, but it has it in its input. Fooled myself here. Then when it comes up with this chain of thought, with the thinking, with the reasoning, then it, of course, also takes into account the tools, the things that actually the agent can do for it. And if the agent says, I can do a web search, then maybe the model just tells the agent, well, then just go and ask Google what's the square root of 4. But in this case, the agent can't do that. And that's why the model says, write a script, execute the scripts, return it to me. So this is the way how it works. And the model, after it has the instruction, it starts to execute it. The model instructs the agent to do a tool call. So the agent only starts to execute these things when the model tells it. So the model is still in the driving seat, and the model is really controlling, telling the agent what it has to do. And there is then like a ping pong, as you see here. At first the model says, write to a file, execute the file, and then give him back the output. And then only at the end can the model tell the agent, square root of 4 is number 2. We very often call this what I named as a ping pong. That the proper term is the agentic loop, because these things, they are just running between each other. And it would be nice, I mean, the human just sees thinking, but it would be nice before the agent starts to write to the file system if it gets the permission from the human. So that's why the agent is usually, and I'm sure you have seen this already many times, especially as developers, where the agent is asking us, can I do this? Can I do that? And much, much more. And this is then what we call the human in the loop, where the agent is really asking for permission to do that. So these agent and tools, they are fixing this limitation. They're giving the model actually a body to do things except in just producing text. In some way, you can also see the model as the brain which thinks, and the agent are the arms, the legs, and whatever you can use of your body to do certain things. So that was a huge milestone step forwards when tools and agents were introduced, because then the model can really do a lot of stuff. The other limitation is about the data actuality. So there is something which we call the cut-off date of models. You can look it up in the system card of the models. But in the end, somehow the model should not only rely on the data it has been trained on. There should also be the option to feed the model further data. So we can, for example, fine-tune our own models. As I said in the beginning, the pre-training is something in a training phase which you will never do because it's just too many resources. But fine-tuning is something which, given you're in enterprise field or you have a very small region, you can also do it on your own. There are open weight models. You can look them up on the internet. You can download them, and you can run your own training on them. Which is, I would say, this is already hardcore, but you can then really train the model on data which it has not seen before. What we see more often is RAG. RAG means Retrieval Augmented Generation, and this is a process where we can access certain external information, data sources, and there are then certain ways on how that information lands, let's just say in the prompt, and then the model where the inference can process it. I just want to mention, if you are interested in RAG itself, but we already have an ebook, a free ebook on various AI, which you can download, and it covers RAG in much detail. Another thing is also in-context learning, where we tell the model in the prompt about the use case. So for example, if I'm a software developer, I can tell the model about a certain functionality which it is not aware of. So kind of I'm training my model in the input itself, in the prompt itself. That is an option. And we very often see this also with skills, because this is the same thing. The skill gets loaded into the prompt. It contains certain description on how certain things needs to be done. For example, I could have a skill where I say, this is how you can, I don't know, create subtitles for a given audio file. These are the applications that you need to run. These are the scripts. This is how it works. And then I'm loading all that information into the model, and then it can make use of it. And the last limitation is then the context size, which, as I said before, is quite critical, because at some point in time, the model just can't run inference anymore. There is too much of information, and then it's just game over. And there are now multiple approaches for that problem. For example, when it comes to memory, we can take our conversation history, put it into an external database, data store, and then the model can use RAG to retrieve certain information from that memory if it needs it. That is what RAG can actually be used for. RAG is also, for example, used for IDEs. For example, Cursor, they can do RAG on our code base as well. So we don't have to load all the code base into the model. That would be too much. But with RAG, it can be optimized, what the model currently requires. Skills is another way on how to deal with the limitations of the context window. Because with skills, the way how it works, that the agents are aware of the skills. And skills always are split up into two parts. There is the so-called metadata, so to say, and then there is the actual skill, which can have a lot of text. And as you remember, this is again with the tooling, the agent needs to tell the model about the tools that it offers so that the model knows what actually tool it can ask for. But with skills, I don't have to load everything into the model at once. I only tell the model about the existence of that skill by telling the model the name of it and also a little bit of a description. So the model has the idea, and if the model decides to load in the skill, because now it requires it, then it can do a tool call where then the agent loads the complete text into the prompt itself. Divide and conquer in some ways is also an option with multiple agents. You can run them in parallel, which means you have multiple sessions. Each session has its own context window, but you can also run them in a hierarchical way. For example, you have on the top, you have a very abstract agent, so to say. So the agent doesn't really go into details. It doesn't overload the prompt with all the details, but it can then delegate to specified agents, which again have their own context window, and there they can go into detail and really put a lot of tokens for their specific task into that context window. That is something that also works. Generally speaking, the vendors also do as much as they can. Of course, they earn their money with token consumptions, but also inputs. But there is, for example, caching included, especially for conversation history. That absolutely makes sense, because I know already the history will always be the same, and inference was already executed on the history. So I can cache these things, the output, which happens, and the price is then also cheaper if it's cached. And you can also do compression, which the agents can do for you automatically as well. So if you reach a certain size in the context window where you or the agent decides that now it becomes critical, then it can take it, summarize it, open a new context window, and load the shorter version into it. That's the way how it works. And I think that with that in the future, that this context management will be something which our agents are more and more doing automatically. Careful still, we are not in the future, by the way, we live in the present. So always careful with those predictions. Context, there are studies out there which say if the context goes beyond 25%, then there is a high risk of hallucination. Then the input is just too much, where the model, of course, sometimes doesn't know what you actually want from it. So it's like if you're listening to someone who talks to you for half an hour, and then the person says, yeah, what do you say? And then you say, yeah, there's so much information which I have just consumed. I don't know what you actually want from me. And then we usually maybe refer to something which was said at the beginning, or maybe actually quite at the end. And this is also what the models are doing, which means they very often can forget or just skip things which were said or which were written in the middle. And this is what this phenomenon is also called lost in the middle. There are also other terms for that. You can look it up: context rot, or catastrophic forgetting, or the needle in the haystack. So there are certain studies about that problem here as well. But this is something that you should also keep in mind. So a quick summary. Models get tokens in and puts tokens out. Input, output. That's the only thing that the model can do. We call that process inference. The model has to be trained. That's the generation of the model. And we differentiate between 3 different main training phases. We have the pre-training, which is the largest one. We have then the fine-tuning and the reinforcement learning. Pre-training can always be done unsupervised, which means we don't need a human sitting by, but for the other training phases, there is some human involvement always there, but also part of it are already done, again, unsupervised, where the AI can do certain reward things on its own. The model has also limitations because the model can only produce text. It can't do anything. And this is where the agent is quite important, because the agent says or can offer certain tool calls to the model. And then the model can call the agent and can say, you do this or that for me. We also have a problem with the data actuality, that the model sometimes needs to be aware of certain data which it has not been trained on. There are multiple ways on how we can do that. Again, agents play an important role here, but also RAG is a very special form. And the context size. Please be aware, you can't just load everything into a model or for an infinite amount of time. There are some limits, and if you exceed 25% of context window, at least to older studies, you already running the risk of hallucinations, meaning the model starts to say something which you see as the wrong thing. Again, I explained that hallucination is more like a relative thing, because the model doesn't really know, it doesn't really understand, which means it can also not really lie to you. It's more or less about predictability, probability things. So these are the things, so these are the limits, and I hope that by now you do have a better understanding of the way how those models work. If you have any questions, any feedback, or if there are certain topics where you want us to create videos or write articles as well, then please let us know. And again, I want to highlight that we at Soverius AI, we focus on the common AI challenges of modern enterprises, like local LLMs, RAG, harness engineering, but also agentic development. So if you're interested for more, then I would highly recommend to subscribe to the channel, and maybe even more important, to visit our website and to subscribe to our newsletter. We will provide more information in the upcoming future. We also have plans to provide a webinar, and in the second half of this year also come up with workshops. Of course, we're also doing consulting, but in the end, please go to our website, subscribe, and you will be notified whenever something new comes up. That's it. Thanks for watching, and goodbye.